So I'm going to tell you about how we use black holes as a theoretical tool to study quantum gravity. And there are many different ways of using black holes to connect to quantum gravity. It's a large subject, and there's a lot of different routes we could take through it. So what I'm going to do is to focus on one corner of this and my own path through the subject in the last few years. And so what I'm going to do is to tell you, I seem to have a, sorry, is to tell you a story about three problems and the surprising connections between them. So these three problems come from different areas of physics and mathematics, and they appear to be completely unrelated. The first one is black holes in the theory of quantum gravity. The second one is the Bootstrap, which is a technique in statistical mechanics and quantum matter. And the third is the sphere packing problem, which is an old problem in mathematics. So I'm going to start the story with black holes. So a black hole, of course, is a region that we typically think of as a collapsed star that's so dense that even light can't escape. But what's really shocking about black holes is that black holes are really featureless objects. They're not really, you don't really need a black hole to be made of anything. Okay, so unlike a star is made of many small parts. A black hole is just pure space-time curvature. So in Einstein's theory of general relativity, gravity comes from the curvature of space-time. And a black hole, which is the most extreme example, is a region where space-time itself is just so curved that it doesn't allow light to escape. And that's a feature of the space-time itself. You know, after the star collapses, the star collapses long after it's gone inside the black hole. That star is really not playing any role. We just have space-time curvature, and that's the black hole. So according to the classical theory of general relativity, Einstein's theory of gravity, in fact, black holes are extremely simple. There's a unique way to make a black hole of a given mass m and spin j. Well, that's what you find at first glance, but if you look closer, then you find a surprise. And this goes back to calculations that were done starting around the 70s. So they did a calculation where you throw some waves at a black hole. So you can throw some waves at a black hole, and some of them fall in, but some of them scatter off the black hole, and you can use that as a probe to understand what's going on with the black hole. So some of it comes out. You can calculate what comes out when you scatter something from a black hole. And what they found was a mystery, a surprise. The mystery is that black holes obey the laws of thermodynamics. And this comes not just from these scattering calculations, but from other calculations done around that time, for example, by Stephen Hawking, who showed that black holes have a temperature. He showed that black holes radiate like a hot object. Black holes also have an entropy. This came from these same calculations, the conclusion that black holes have an entropy which is enormous. So this formula on the screen for the entropy is a fascinating formula that says that the entropy of a black hole is given by its area, but it's area in Planck units. So it's area in units of the Planck length, which is 10 to the minus 35 meters. This is an enormous number. Okay, so there's a black hole at the center of the Milky Way called Sagittarius A star. That now there's a lot of observational evidence for this black hole, and that black hole, as an example, has an entropy of 2 to the 88. So that number might not be very meaningful to you, but the entropy measures how complicated an object is. Okay, so it measures how many parts it's made of and how complex it is. And that number, 2 to the 88, That's about the same as the entropy of all the known matter in the observable universe. Okay, so this is an enormous amount of entropy that tells us that black holes are extremely complex. They're made of a very large number of parts, which is a mystery, because I said just a minute ago that black holes aren't made of anything at all, that black holes are just featureless objects. So the mystery is understanding the origin of this complexity, understanding what it is that black holes are made of and what gives you this enormous entropy. Well, we think the interpretation of this is that the complexity must come from the quantum theory. So in Einstein's classical theory of gravity, black holes are featureless objects. But we think that in the quantum theory, they must be extremely complicated. And that if we were able to zoom in to the Planck length, 10 to the minus 35 meters, that we would see some structure there and some bits that are making up the black hole, some microscopic degrees of freedom. Those have to be quantum mechanical, which is what these symbols represent on the slide. So the interpretation of this large entropy is that black holes are made of some very complex, strongly interacting quantum constituents down at the Planck length. Those constituents are not understood. So this is a conjecture. This is what we believe based on a lot of evidence and based on these laws of black hole thermodynamics. But it's still something we're trying to understand. So the analogy to have in mind here is something like a fluid. Okay, so thermodynamics, the laws of thermodynamics, apply to objects with lots of moving parts. Like the gas in this room obeys the laws of thermodynamics because it's made of lots of molecules. And individually, those molecules are behaving erratically. But together, the average statistical properties of that gas gives us the laws of thermodynamics. So the idea with black holes is that there's some quantum pieces of the black hole that are interacting in some very complex way that give us the laws of thermodynamics that we see when we do these calculations of scattering something against a black hole. Now, this is really, so this is, for a physicist, this is a real gift, okay? Because we can't make a black hole in the lab. We can't make one and cut it open and see what the pieces are. We can see them in the sky, but not at high resolution where we'd be able to even begin to answer questions like this observationally. But what it means is that we can, just using the theory of black holes, learn something about very short distances and the theory of quantum gravity from their properties. Now, if this is true, which we think it is, then the consequences of this really reach beyond just black hole physics. Because as I explained, black holes are pure space-time. They're just made of space-time curvature. So if black holes are made of something more microscopic, then actually space-time is made of something microscopic. So space-time has to be made of something. And the consequence of this idea is really that we have to think of space-time itself as an emergent phenomenon. That the Einstein equations of relativity, the equations of gravity, describe then some long-distance collective excitations in that of those microscopic constituents. A rough analogy would be the Navier-Stokes equations of hydrodynamics. So a fluid is made of these many parts, but at long distances, we use the theory of hydrodynamics to describe it. And it could be that Einstein's equations of general relativity are playing a similar role. So this gives us a very useful way to think about the theory of quantum gravity and the problem of what it means to look for a theory of quantum gravity. We don't have a complete theory of quantum gravity. We have candidates. We have a lot of ideas from string theory, but we don't have a complete theory. So thinking about black holes has given a way to think about this problem that's been very productive over the last couple decades. The standard or traditional way of phrasing the problem of quantum gravity is to ask how is gravity reconciled with quantum mechanics at very short distances? Well, this is correct. This is what it means to find a theory of quantum gravity. But from a modern viewpoint, I like to pose the problem of quantum gravity differently. I like to say it's the problem of understanding what are the atoms of space-time and how do they interact. And I mean atoms here in the ancient Greek sense of the indivisible constituents. So what are the atoms of space-time and how do they interact? Well, we don't know, but a partial answer to this was provided about almost 25 years ago now, and is known as holographic duality, or the ADS-CFT correspondence. Holographic duality is a way of thinking about and understanding certain black holes in a theory of quantum gravity. It gives you another description, a dual description. And what holographic duality says is that in certain situations, a theory of quantum gravity with black holes, it's the image on the left, is exactly equivalent to a theory of quantum matter without gravity. That's what this image represents on the right. Okay, so that there's a different, in some situations, when we have these very complex black holes in quantum gravity that are very difficult to understand, we have another way of thinking about it as quantum matter. Now, quantum matter is also a very difficult problem, but it's in some ways simpler than the problem of quantum gravity. In holographic duality, black hole thermodynamics and some of these mysteries that were discovered in the 70s and 80s is explained as the ordinary thermodynamics of the dual description. The mystery was, what are all the microscopic bits of what are all the microscopic pieces of the black hole that are responsible for this complexity, for the large entropy? And the answer in this case is that it's provided by this quantum matter. This duality is what's known as a strong-weak duality. What that means is that often problems that are hard, questions that are hard, calculations that are hard on one side become easy on the other side. Not always. Sometimes things are hard on both sides. But often it takes a hard problem and replaces it by an easy problem in the dual description. And that's why dualities like this have become such an essential tool. And that brings us to the second part of the story, which is the conformal bootstrap, which is the second of the three pieces that I want to tell you about, and then we're going to tie them together. So I need to explain what the conformal bootstrap means. First of all, a conformal field theory is a theory of quantum matter, a quantum field theory, with an extra symmetry under distortions of space-time. This is called conformal symmetry. So we take space-time and rotate and distort it in some way. And these distortions can be done in many different ways. But the theory has a symmetry under these distortions. It's insensitive to the distortion. Now, this sounds very special. Why should a theory be insensitive to distortions of space-time like this? Well, actually, it's not that special. It shows up all over the place in physics. This is a phenomenon known as universality. But it shows up in particle physics. It shows up in the theory of phase transitions. It shows up in condensed matter physics and in the theory of black holes, as I'm discussing today. This picture that I keep showing represents the long-distance correlations that you get in matter near a phase transition. So this is one of the examples of a physical system where you get a conformal field theory. So that's a conformal field theory. It's these special theories of matter with this extra property. Now, the conformal bootstrap is a technique to analyze strongly interacting conformal field theories. So strongly interacting just means that the constituents are interacting with each other a lot, and these are the kinds of theories that are very difficult to analyze with traditional methods. So it's a technique to analyze these strongly interacting theories that starts from the question, what predictions for physical phenomena follow from symmetries and quantum mechanics alone? This is sort of the philosophy, the bootstrap philosophy, it's called. And it sounds sort of too good to be true, but in fact, the bootstrap approach, unlike most techniques in physics, the bootstrap approach doesn't require knowing in advance what something is made of. Okay, so in other words, you don't need to know the Hamiltonian that describes the system. So you don't start out by saying what it's made of and then solving it the way we ordinarily solve physics problems. We don't do it that way. It's an opposite approach where you just say what the symmetries are, and you invoke quantum mechanics and relativity and the symmetries, and maybe some other input. For example, we're going to use input later that there are black holes in the theory, but that's it. So you just start from that, and then it turns out, very surprisingly, it turns out that in many cases that's a powerful enough set of inputs to predict physical phenomena, and in some cases to completely solve a theory exactly. So this is an idea that goes back a long time, the bootstrap idea, but it was reinvigorated around in the last 10 to 15 years with the discovery of powerful new computational methods and new applications that came out of these methods. It also led to the Simon's collaboration on the non-perturbative bootstrap, of which I'm one of the PIs. So the bootstrap has a secret sauce, a key ingredient, and that secret sauce is called crossing symmetry. So crossing symmetry is a property of relativistic physical systems, which is very surprising, and here's how it works. So what I'm drawing here is a scattering, is a diagram that's going to show two particles scattering. So we start out with two red particles, which are separated in the space direction, and we throw those particles against each other. The particles collide, and they interact in some way. I'm representing that as them turning into blue particles, just for visual purposes. So they change into some other particles, and they bounce off, and they scatter. So that's some physical process that describes two particles colliding, interacting, changing in some way, and scattering off of each other. Now, where crossing symmetry comes from is that we can take this diagram, we can take this picture of what happened, and we can reinterpret it by turning it sideways. Okay, so let me show that again. We're going to take this picture. Space is going this way. Time is going upward. And we're going to take that picture and rotate it in a way that switches space and time. Now we take that picture and reinterpret it as a different scattering process. Okay, so we take this picture, And we interpret this as a blue particle scattering against a red particle. Again, those particles bump into each other, they interact, and they come out. And in relativistic theories, these two things are related to each other. In fact, these two different physical processes have the same probability for occurring. So this is called crossing symmetry, and it tells us that these two physically different things, two different experiments that you can do, have the same outcome, the scattering of the two red particles or the scattering of the red versus blue. So that's crossing symmetry. Now, I actually need to use something that's even more complicated than crossing symmetry. This one I'm just going to give a quick flavor for, but it comes from the same idea. Okay, so since we're talking about black holes, and black holes are not just made of one piece. Okay, I just talked about scattering one particle against another. Black holes are made of lots of pieces. So we need to think about hot gases made of lots of particles. And when you have a hot gas like this, then if you're in two space-time dimensions, you can think of it as this picture where you have lots of particles bumping into each other. So this is just supposed to represent many different scattering processes where you have lots of particles flying around and bumping into each other. And again, you can reinterpret that picture. So you can take this picture of particles scattering in a gas and turn it on its side and reinterpret it in a different way. What that gives you is a surprising result, which is a temperature inversion symmetry. Okay, so theories like this are actually invariant under taking the temperature and replacing it by the inverse temperature, 1/T. This is a symmetry that relates hot things to cold things. It's a hot-cold symmetry, which is a bizarre feature, but it's true in these sorts of systems. So that's the physical input that we're going to use. We're going to use this hot-cold. So remember I said the Bootstrap philosophy is that you start with some basic features of your system, quantum mechanics, relativity, and some symmetries. Well, this is the one that we're going to rely on. We're going to use quantum mechanics, relativity, and this temperature inversion, hot-cold symmetry. And we like to package this into a function called the partition function. And if you're familiar with that, then I'm writing it here just to tell you what we use. But otherwise, you can just think of this temperature hot-cold symmetry. So the partition function is just a way of packaging the physics into a convenient way, packages it into a nice function. And what this hot-cold inversion symmetry tells you is that function z of t is equal to z of 1/T. This is known as the Bootstrap equation, and it's what we're going to use soon. Now, by holographic duality, which is this relationship between quantum matter and black holes, we know that black holes also obey the Bootstrap equations. So the Bootstrap equations were invented for studying quantum matter. But because of this relationship between quantum matter and black holes, they can also be used to study black holes. And what this does is it maps an abstract physics problem, the problem of finding consistent possible theories of quantum gravity. That sounds very abstract, but it replaces that abstract problem by a very concrete math problem. This question becomes, find crossing invariant functions that obey the Bootstrap equations. And there are some other inputs that you have to impose, which I won't go into, but that amount to asking for these asking for it to have the right physical properties in order to have black holes. And this has led to a research program of bootstrapping quantum gravity, of approaching the problem of quantum gravity through these bootstrap methods. And that is one of the, so this is a research program that's been pursued by many people over the last decade or so, and this is one of the focus areas of the Simons Bootstrap collaboration. The goals of this program broadly are to understand how general relativity emerges from microscopic physics at the Planck scale, to use gravity as a tool to study fundamental properties of quantum matter. Strongly interacting quantum matter is itself a very important and difficult subject. And sometimes, because of this strong-weak duality that maps easy problems to hard problems and hard problems to easy problems, sometimes we can take a hard problem about quantum matter and solve it using black holes. The black hole in that case is just a trick. It's something that we introduce to solve a hard problem in quantum matter. And third, to constrain the landscape of possible theories of quantum gravity. As I've emphasized, we don't have a complete theory, but we're trying to pin down what the possibilities are to explore what the different theories could be. Okay. I'm now going to focus on one bootstrap question, and we're going to talk about this bootstrap question for the rest of the lecture. There are many different ways of applying the bootstrap to quantum gravity. There are many different examples that I could talk about, but I'm going to focus on this one. And the question is the following: what is the simplest consistent theory of quantum gravity in 3 space-time dimensions? In particular, is it Einstein's theory of general relativity? That's one possibility. Or is it something more exotic? Does it require things like supersymmetry, which many people have theorized? Or does it require string theory? Does it require extra dimensions or exotic objects known as branes? Well, this question is not yet answered, but I want to see where it leads us. It's going to take us somewhere interesting. Before I go on, let me say why we're talking about 3 space-time dimensions. So we live in 3 space dimensions, so we live in 4 space-time dimensions. But the problem of quantum gravity in 4 space-time dimensions is more difficult. And we can simplify things a bit by looking at models in 3 space-time dimensions. And so the idea is to try to solve that problem first and see what we learn, and hopefully be able to apply it to more realistic theories like our 4 dimensions that we live in. Okay, so I want to take this problem, what is the simplest consistent theory of quantum gravity in 3 dimensions, and apply the bootstrap methodology to this question. So a theory of quantum gravity alone, we want to ask whether we can have quantum gravity that's just gravity without any extra stuff in it. So no extra particles, no strings, no extra dimensions, nothing extra, just gravity alone. Well, if you had a theory of gravity alone, then it would only have black holes. There would be no other particles. There would be no particles at all below the Planck scale. And so you would just have a theory of black holes and whatever it is that black holes are made of. So we're going to try to use the bootstrap to look for theories with the following properties. First of all, there has to be a large number of degrees of freedom. Remember that enormous entropy of a black hole like Sagittarius A star. That enormous entropy is telling us that we should be talking about theories with a very large number of degrees of freedom if we are to have any hope of explaining the black holes that we see. So that's the first property. And the second one is that we want the lightest object to be as heavy as possible. This is what I mean by simple. Okay, if you have a theory of gravity with lots of extra stuff in it, lots of branes and extra particles and strings, then there would be lots of light stuff of low mass. A simple theory is one where you just have black holes, and so the lightest black holes are rather heavy objects, and we're going to use that as a way of looking for the simplest theory. And finally, we're using this bootstrap method, and I described for you the bootstrap equation that applies to these sorts of theories when they're at some temperature T. So we're looking for theories that have a large number of degrees of freedom, that have their lightest object is very heavy, so they don't have very much low mass stuff. And finally, they're consistent with the bootstrap equation that relates hot to cold. This has mapped a problem of finding theories of quantum gravity to a problem of finding functions with this property. Okay, so that's the power of the bootstrap, is that you take this problem of going out and looking for physics theories, and you replace it with this math problem of finding functions that satisfy the properties that you want. And that's a problem that, well, I mentioned these new powerful computational methods a few minutes ago. And what those methods can do is they can tell you what kinds of functions can satisfy these properties. So that's what the computational methods are for. And so I'm not going to go through how that's done, but the upshot is that you can put this problem on a computer, and now you can bootstrap on a computer the simplest theory of three-dimensional gravity. So what I'm showing here is the results of running that computer program. The horizontal is the number of degrees of freedom. You'll notice that number is small. It's not 10 to the 85 or whatever giant number I had before. That's just because the computations become more difficult as the number of degrees of freedom increases. So we start at a small number of degrees of freedom, and we work our way up. So I'm just showing the answer when that number is small. And then we ask, how heavy can we make the black holes? Okay, and what that red line tells you, the bootstrap bound, is that's the heaviest you can make the first black hole. So every theory of this type, every theory of quantum gravity, has a black hole below the red line. That's what the red line is telling you. That came out of doing this bootstrap computationally. So that's the red line. Now, so below the red line, those dots that I put there, those are known theories, known conformal field theories. Specific examples that people have studied where you can write down all the parts, and you can say what the degrees of freedom are, and you can solve for the dynamics. So, of course, if we did things correctly, the existing theories, the known theories, have to lie below the bootstrap bound, and they do. So that's good. But what you also see here is something interesting happening. That's happening at certain special numbers of degrees of freedom. So in this case, the bootstrap bound is exactly saturated. It's exactly equal to the mass of the lightest object in a known theory when n is 4, and also when n is 12, the number of degrees of freedom. So that's something interesting that I'm just observing at this point, and we're going to come back to it as we go on. That's right. This comes out of the numerics. Well, so far it comes out of the numerics. I'm going to explain it as we go. It first came out of the numerics. Yeah. And there's a not only does it agree, there's a hint of something really surprising and magical happening here, which is the following. So when we put this on a computer and ran it at n equals 12, and there's a similar story at n equals 4, the result for the energy of the lightest black hole was this number that I've written here, and this number could have been anything. Okay, we didn't put in that this had to be a whole number, so it could have been any decimal, but we ran it on a computer and found that the lightest black hole was essentially of mass exactly equal to 2 to something like 50 decimal places. This is just coming as a surprise out of the numerics. And furthermore, you can not only calculate the energies, it turns out that you can calculate how many of these light black holes there are, again numerically. And the number we found was, to very high accuracy, 196,884. Okay, so that number might not mean anything to you, but it's a famous number because it's 196,883 plus 1. And that number is a famous number in mathematics. So that number is associated to a mathematical object called the monster group. The monster group is a very complex object that has a habit of showing up in areas of mathematics where nobody ordered it. It's showing up as a surprise. It's happened before in other areas of math and physics. And here we see it happening again, that we were just trying to look at these black holes and understand how heavy they could be, and out came this number mysteriously associated to the monster group. And that brings us to the third part of the story, which is the sphere packing problem. So the sphere packing problem is an old problem in geometry. The problem is stated here is what is the maximal density of non-overlapping spheres in n dimensions? So I've drawn it here in 3 dimensions. Imagine you're stacking oranges. That's the sphere packing problem. So it sounds simple, but this turns out to be an incredibly deep problem in mathematics that has connections to all sorts of areas of math and physics. It's connected to the theory of lattices and groups. It's connected to the mathematical theory of modular forms, to the theory of error-correcting codes. In fact, sphere packing has been used to design error-correcting codes that are actually used, that at least have been actually used in modems or cell phones, although as far as I know, they aren't anymore. It's even been suggested to show up in biology, and we're going to see that it plays a role here in our study of conformal field theory and quantum gravity. So the sphere packing problem has a bizarre feature that it just seems to be very different depending on how many dimensions you're in. Okay, so the simplest case, the simplest case, I suppose, is 1 dimension, where it's trivial. The simplest, slightly non-trivial case is 2 dimensions, where you're just tiling circles. Okay, so a sphere in 2 dimensions just means a circle. And so in 2 dimensions, the sphere packing problem, the sphere packing question asks how closely you can pack a bunch of circles onto the page. And the answer to that question is the hexagonal lattice. This was proved a long time ago. Where things get really interesting is when you go to 3 dimensions. So this is known as the Kepler problem. It was actually, the history is fascinating. So this was actually a problem that was posed by Sir Walter Raleigh when he was trying to stack cannonballs on a ship. Okay, so this was a very practical math problem when it was first studied. And he posed this question to a mathematician friend of his, and somehow it ended up in the hands of Johann Kepler. And Kepler was unable to prove it, but made the conjecture that the most efficient way of stacking a bunch of cannonballs was the face-centered cubic lattice, which is pictured here. So this is known as the Kepler conjecture, and it was made a bit over 400 years ago. Mathematicians started studying this problem in earnest maybe 150 years ago and made progress on it over the years, but it turned out to be an incredibly difficult problem. And it wasn't solved until a proof by Hales in 1998. This proof was a real tour de force, so it's hundreds of pages long, and that's just the part you can read. So there's a computer-assisted part. So it involves computer calculations in addition to the written part of the proof. And that computer-assisted proof is now accepted, but it took 11 years just to verify the proof. Okay, so this is an extremely complicated argument with a lot of computation involved. So it came as a real surprise to the mathematics community when there was a breakthrough in 2016. So in 2016, after essentially 400 years, only the cases of 2 and 3 dimensions had been solved. And then in 2016, Marina Vyazovska announced the solution of the sphere packing problem in 8 dimensions. So in 8 dimensions, the solution, the densest packing of spheres, is something called the E8 lattice, which I won't try to draw. I can't draw pictures in 8 dimensions. But it's a fascinating object that had been, a fascinating arrangement that had been studied before.
These are 7-dimensional
So
spheres?
it's in 8 Euclidean dimensions. So the spheres are, yes, that's right. Yeah. So Vyazovska announced this result in, I think it was March of 2016, and then teamed up and with some collaborators just 1 week later solved the case of 24 dimensions. So all of a sudden, these higher dimensional problems fell. First, n equals 4 dimensions, where the answer was the E8 lattice, and then using the same methods that had been applied by Vyazovska for 8 dimensions, they solved the problem in 24 dimensions and found that the densest packing is something called the Leech lattice. Now, the Leech lattice is related to the monster group, and that's going to tie things back together. These proofs of Vyazovska and collaborators rely on an earlier result known as the Cohn-Elkies theorem, which I'm going to tell you a little about, because we'll see that this theorem of Cohn-Elkies is in fact an instance of the conformal bootstrap. So what we're going to see is that actually physicists and mathematicians had both been studying this problem unknowingly at the same time. So the Cohn-Elkies theorem, which I won't go into detail, but I just want to give you some flavor for what it says or how it works. So the idea, much like the bootstrap, is to turn a problem, in this case about spheres, into a problem about functions. So what Cohn-Elkies did was they defined a function, f, associated to a sphere packing. And the way you should think of that function is that it tells you properties of how far apart the centers are. Okay, so a sphere packing is just a bunch of spheres arranged in some way. And you can measure the distances between all their centers in the whole sphere packing. And you can use those to you can put them all together into this function f of Cohn-Elkies. What they showed is that properties of the function f translate between properties of the sphere packing. So this turns a problem in geometry to a problem of finding functions. What they showed is that if you can find a function, so this now becomes a problem of looking for good functions that can show the properties that you want. In particular, they're trying to look for the densest possible configuration of spheres. So there's some procedure to look for the associated function. But it's very hard to find these functions. You need a function with some very strange properties. And it becomes a problem of solving this difficult question of how to find the function. But much like in Bootstrap, it's a problem that you can put on a computer. And this was done by Cohn-Elkies in their work back in 2003. So in this case, so we have a similar plot to what I showed in the physics problem. But now we're talking about sphere packing. And what this result shows is the following. So this is the result of Cohn-Elkies. On the horizontal is the dimension of space. Okay, so the first one, I think, is the two-dimensional sphere packing. So that's the hexagonal lattice. In 3 dimensions, this is the Kepler problem. So that's the stacking bowling balls that I showed. And then we go up from there. And the Cohn-Elkies theorem says that if you can find a function with certain properties, then you can derive a bound on the density of all possible sphere packings. And that bound is the red line. Okay, so what this plot says is, so the vertical is density, or density rescaled in some way. So what Cohn-Elkies showed was that the red line here, which is determined by a computer program, is an upper bound on the density of any sphere packing. All sphere packings have to lie below the red line. The blue dots are the densest known sphere packings in various dimensions. So down at the bottom of the plot, we have the solved cases. Well, at the time, the only solved cases, which were the hexagonal lattice and the Kepler problem in 3 dimensions. But what they observed was that their bound hits known lattices, known sphere packings, also in 8 dimensions, where the bound hits the packing density of the E8 lattice, and in 24 dimensions, where their numerical bound hits the density of the Leech lattice. It has long been suspected, actually, that these might be the densest sphere packings in 8 and 24 dimensions. But there wasn't really overwhelming evidence for it. It certainly wasn't proven, and there wasn't overwhelming evidence for it until this numerical result of Cohn-Elkies. But since they were doing this numerically, they were unable to turn this into a rigorous mathematical proof. It seemed like overwhelming evidence that these must be the best possible sphere packings in 8 and 24 dimensions. But the numerics can only be so accurate. So what they actually showed was, well, if you look more closely, the blue dot is about 1 in 10 to the 50 below the red line. Okay, so by mathematics standards, that's not a proof. So what Wiazowska did in 2016 was to find the magic function f of Cohn-Elkies. She found a function with just the right properties to prove this exactly. Just the right properties to use in the Cohn-Elkies theorem. So it's the same function that they found approximately in their computer program, but they were doing numerically and could only find it approximately. Wiazowska found it exactly by analytic methods. And she used some combination of a very inspired guess and some beautiful mathematics of modular forms. So now it's time to go back and to tie these three pieces together. So how are black holes, black hole thermodynamics, the conformal bootstrap, and sphere packing all related to each other? Well, I've been hinting at how they're related throughout, but now I can come out and say it. So the statement is that the conformal bootstrap, as I described, for finding the simplest theory of three-dimensional gravity, is exactly the same math problem as these bounds of Cohn-Elkies on sphere packing. In both cases, we're trying to find functions that satisfy some magic properties. We both have reduced this problem, the problem of finding simple theories of quantum gravity, or the problem of finding dense sphere packings, have been reduced to the problem of finding functions with some special properties. And in this case, it turns out that really we're demanding the same thing. We've turned this into the same math problem. So these two pictures that I showed are actually essentially the same picture. So the first one I showed was the bound on the lightest black hole in a theory of quantum gravity. So that red line there is the bootstrap bound. And the second picture, the second plot that I showed was the bound on the sphere packing density using this method of Cohn-Elkies. And the statement is that those red lines are exactly the same red line. They're precisely the same. So bounds on black holes in quantum gravity and bounds on sphere packings actually map to each other. Everything about these two problems maps. So in quantum gravity, we're especially interested in a very large number of degrees of freedom. Well, in sphere packing, that corresponds to packing spheres in a high-dimensional space. The number of degrees of freedom in the theory of quantum gravity become the number of dimensions of the sphere packing. So now we're talking about very high-dimensional spheres in a high-dimensional space. The very simple theories of quantum gravity, the ones we were looking for with the bootstrap, very nicely map to the densest sphere packings. So a simple theory of gravity corresponds to a very dense sphere packing. So not only were we looking at the same sort of math problem, it turns out we were both trying to do the same thing. We were trying to find simple theories of gravity. They were trying to find dense sphere packings, but actually this was the same problem. And this is all quantitative. The question I posed about what is the simplest consistent theory of quantum gravity in three space-time dimensions translates into a bound on the mass of the lightest black hole. And the problem of what is the densest packing of hyperspheres in a large number of dimensions, well, there's a numerical bound on how big that density can be. And these bounds turned out to be exactly the same bound after you translate between these two problems. So this has been great fun, because now we're working closely with mathematicians to try to push this program further. So they have, in some sense at least, been studying this problem for 400 years. We've only been doing the bootstrap for, well, 50 years or 10 years, depending on how you count. So we have a lot to learn from them. But we also have something to offer to the mathematicians in that we have this physical way of looking at the problem. And this gives us, anytime you have a new way of looking at a problem, surprises are bound to come up, and you can find lots of interesting new ways of thinking about it. Okay, so I'm going to conclude with some outlook on the big picture. I've discussed our efforts towards understanding the simplest theory of three-dimensional gravity and how we've used the bootstrap to obtain new constraints on black holes in quantum gravity. We haven't yet cornered the theory. You know, the way I motivated at the beginning was that we want to use quantum mechanics and relativity and the temperature inversion symmetry, crossing symmetry, to try to pin down the physical properties of quantum gravity. Well, we're not there. We've derived some consequences of these inputs, but we still don't know, for example, whether strings are required, whether string theory is required, or whether there are other possibilities. So that's something that we hope to be able to do by applying the bootstrap to quantum gravity. And secondly, I've described connections to sphere packing in high-dimensional space, and these surprising relationships between the three subjects: conformal bootstrap, sphere packing in geometry, and black holes in gravity. The bigger picture in terms of quantum gravity and the bootstrap is to try to ask the question, or rather to try to answer the question of what's possible in a consistent theory of quantum gravity. I think this is especially important because we're trying to study physical phenomena, but these are physical phenomena that are at present very difficult to probe with experiment. Okay, so the experiments that we would need to do to probe quantum gravity are simply too difficult technologically. There's no problem in principle, but the technology is not there, and it's going to be a long time before we can probe these things experimentally. But what we can do is to ask, what are the possibilities? And it turns out that this is extremely constrained. Okay, if the answer was that pretty much anything goes, then we'd be out of a job, and we wouldn't be able to really say anything. We just have to wait for the experiments to come along and tell us what the right answer is. But it turns out it doesn't seem to work that way, that just the basic principles that we know, like relativity and quantum mechanics, are extremely constraining. There seem to be very few possibilities for what this theory can look like, so that it becomes useful to ask about looking for all the possible theories. Last but not least, I want to thank my collaborators on this work, and everyone else in the Simons Bootstrap collaboration. I've listed only the principal investigators here because I ran out of room on my slide. This is a collaboration that goes across 15 institutions and several continents, and really consists mostly of students and postdocs. So there's a great community working on these sorts of problems, and not just problems on quantum gravity, but other applications of the bootstrap to other areas of physics. And I'll end there. Thank you for your attention.